Hello everyone. In the following, let us check cell capacity using the queuing system model. To have the queuing system model, we have the parameter assumption. We have F number of multiple stations requesting service with parameter lambda. So that says we have arrival of mobile station to a queuing system. But the queuing system actually it's a cell. Alright, a cell to be modeled by a queuing system. So we should refer to the content talking about traffic theory. And so that we have the person arrival and the exponential service queuing system. So is it an MM1? Actually no. Later we can know what is the corresponding notation for the queuing system. And last one we have the service time. And if we have arrival rate and service time, and rate multiply service time, that says, oh, okay, during the service time, how many arrivals? So we have A. A actually here, it is called the overload. It's a load. And here we have an example. For example, we have this, all right. An average 30 requests are generated during an hour. Alright, and T equal to this. So, according to this, 30 in an hour. So, in an hour, then lambda equal to this. And T equal to this one. So, we can have the calculation for A. Alright, so we have the corresponding lambda. And this is the service time T. Alright. Lambda multiply T equal to this. Oh, okay, it's equal to 3. And equal to 3, this is the overload. The overload, we have the specific unit. And the unit is called Erlang. At this moment, we have the overload. And the unit for overload, we call its unit. So, we can have the calculation using the current given example. And let us continue. Therefore, we have arrival rate lambda. We have actually previously we have service time, but right now we have service rate. So service time actually equal to service rate equal to 1 over service time. And here, how to have the cell capacity model. In fact, we give number of channel S, and the channel, for example, 1, 2, 2S, and channel occupy, and should we have the actual channel? No. If we don't have the actual channel, then we don't have a buffer, no buffer, 0 buffer. And then all the customers should be blocked. And so that we have a person arrival. And how many channels? We have a 1 to S and no buffer. If so, how to have the countdown notation for this kind of queuing model? Actually, it's MMSS. S means S servers. And the next one, so this is number of servers or channels. And the final S serving as a capacity. Capacity include number of channel or number of servers and the buffer. But right now, S, this S minus the previous S equal to 0. So that says we have 0 buffer. So that's why we have an MMS queuing model. And based on MMS queuing model, then we have the system transition diagram. And actually, we can have arrival rate, follow these. And the service rate, here we have the general description. But how to have the corresponding rate? Actually, this one equal to lambda. But this one equal to S mu, S minus 1 mu, and the others. So because of this, then we can have the QE model. This one. I didn't know we have the common rate, arrival rate. So even we have the index 1, 2, 3, but they are the same parameter, lambda. However, for this one, because of one server, so we have a single rate. Two server, we can serve simultaneously. So we have 2 mu to serve as the joint service rate. And likewise, if we have a S channel or server there, we can have the S mu service rate. Well, if we have the state transition diagram like this, how to have the equilibrium equations? In fact, we can follow this. Oh, a cut. And a cut here. For example, I minus 1 and I. So here. So a cut or a cut here. Actually, we have a cut here. So if a cut here, we will have here is lambda. Lambda pi minus 1 equal to I mu multiply probability I. So based on this equation, and also we have the summation for OI. I from 0 to S, it should be equal to 1. So based on this, then we can find the individual probability P sub I. So how to have a probability P sub I? Actually, right now I have my way to have the relationship. This is the initial one, and the ith one actually it should be Pi equal to lambda over mu Pi minus 1. Oh, sorry, it's I mu. All right, I mu, and rearrange it and consider all the probability. Sum of all probability should be equal to 1. So we will have this result. All right, so actually the form follow the previous recursive formula. Which one? Oh, okay, so P1 actually equal to lambda, it's 1. P0. Pi actually is I mu, and lambda again Pi minus 1. So rearrange it, then we will have the results. All right, we will have the result. Okay, so we have this. All right, actually not this one. It should be this one. Why? Look at this. We can have lambda I mu, and this one equal to lambda I minus mu, and Pi minus 2. So tier 0. So finally we should have mu I minus 1 mu, tier 1 mu, and lambda. So we have lambda and mu I square, but here I plus 1, so we have a factorial function. So that's why we have this way. If we assume, oh sorry, it should be, no, something wrong here. It should be this one, lambda over mu. Okay, so A lambda over mu, so we have this. So finally, we have the result. Okay, P of I or Pi equal to A raised power to I. Here we have factorial I, factorial function of I, and P of 0. And summation should be equal to 1. So we can have this way. Summation of all probability should be 1. So finally, we can find P of 0 first. So what is P of 0? This one. Summation for O equal to 1. So it's 1 over this. Once we have this 1 over this, so we can have P of I. So here, remove it, and so that we have the formula. Once we have the formula, then we want to check capacity. Capacity of a cell. So we can check the specific probability P of S. P of S says it's the probability that all channels are busy or occupied. Once all channels are occupied, then we have this called blocking probability. So this probability is a special meaning, blocking probability. Why is blocking probability? If an arriving customer or code C, all channels are occupied, and then their code will be blocked directly. So it's the blocking probability. And this blocking probability we call Erlang B formula to have the blocking probability. Because we can have S, we can have A, so we can have a function B, S and A, so it's the blocking probability. And currently, if we have S equal to 2 and A equal to 3, then blocking probability for the Erlang B formula, actually it should be this. That says we have the blocking probability. If we have the 30 channels, and actually we will have the number of code blocked using the current one. So this is the blocking probability. And we can have the efficiency based on the blocking probability. How to define that one? Alright, so we have the Erlang multiply the non-blocking probability. Non-blocking probability should be 1 over the blocking probability. So the numerator, we can have the number of channel not blocked. But at most, how many? Actually here we have 2. Why we have 2? Because we consider this one. Assume we have S equal to 2. So how many channels? Only 2. But if we consider those blocks not blocked, actually the F number should be 1.4. So that the efficiency serving as a ratio. The capacity actually is the given one, number of channels. Alright, number of channels, but how many? Based on the overload, how many how many channels not, or maybe users not blocked, and so that we can have this ratio. It's 0.7, so we can have the calculation of efficiency. Well, currently we can pass on the MNSS. To have the derivation for blocking probability, so that we can have traffic not blocked, and so that we can have the efficiency derivation. And right now we have the different way to look at this. Any possible probability that a code will be delayed. Will be delayed, that says if we can consider buffer. Previously, we don't have the setting for the buffer. We think if no channel, then all the code should be blocked. But right now, we consider actual buffer. If we have an actual buffer, then we have M and S infinity. Alright, and MMS infinity, this one not the same as the previous MNSS. So we cannot have the blocking probability like previous one. Actually, we don't have the blocking probability for this kind of Kendall notation. But we can find, okay, all servers are occupied or all channels are occupied. Then this is the probability. Code will be delayed. That state will be put into the buffer. So how to have the calculation? Actually, this formula. So this formula calculates the probability. If we still have a probability I, and I larger than or equal to, I greater than S to infinity, and get the summation of the corresponding probability, then we can find this kind of probability of a code being delayed. And this kind of formula we can call Erlang C formula. But Erlang C formula, it doesn't mean it's the blocking probability. Instead, it's a probability of a code being delayed. And this kind of formula we call Erlang C. So next time, if someone that they have the Erlang B and Erlang C, this is a way to have the corresponding probabilities. All right, so this is the corresponding discussion about the cell capacity given number of cells, and also try to have the efficiency based on the blocking probability. So based on the previous formula, in fact, we can have a different value setting. How about s equal to 5, and same we have 3 Erlang, and we can have an Erlang B formula, and so that we can have an Erlang C formula. And Erlang B formula, we can have the blocking probability. And Erlang C a bit larger. Why? Because Erlang C can accommodate customers and ask customer to stay in the buffer. So the portion should be higher than the portion of code blocked. So that's why we have the different value. That's why we have Erlang B and we have Erlang C formula. So this is the summary for Erlang B and Erlang C. Erlang C talking about blocking probability, so we have this formula. And Erlang C talking about code being delayed, so we have Erlang C formula. And are they the same? No, they are not the same. So this is the discussion for cell capacity and blocking probability, or probability of code being delayed. All right, that's it.